Hello to Daryl's Dominion again. Welcome back. This is Chapter 5, Section 2. And this is where we're going to learn about kinetic energy and the work energy theorem and how we can connect work, which we learned in 5.1, to energy. So we're going to go back here to our definition for work, which we just were given last time. Oh, and by the way, if you didn't watch the video on notes for 5.1, you should go back and watch yesterday's video. But from that, we learned that work net equals force times change in displacement. Well, we can take force and we can write that out according to Newton's second law as mass times acceleration. And so then we get mass times acceleration times change in x. And my goal here is to find, using one of the equations we derived from Newton's second law, I'm going to find a substitution for ax related to velocity. So I'm going to go back to this equation here. Final velocity squared equals initial velocity squared plus 2a delta displacement. And then we're going to rearrange it so we have a delta x equal to something. And rearranging that, we're going to subtract both sides by VO squared. And then we're going to divide both sides by 2. And now we have what we were looking for, acceleration times change in displacement equals v squared minus VO squared divided by 2. Well, now that we have that, we can go ahead and substitute that back into the equation we were just talking about. So taking this, I'm substituting that back into my work net equation, and I end up with, instead of mass times acceleration times delta x, I'm going to take this and put it in there. So I get mass times change in velocity squared divided by 2. And then rewriting that, I can get 1/2 m delta v squared, which looks very familiar. So your work net would be the change in velocity, 1/2 m times the change in velocity squared. So this is interesting because now we can connect an object's speed to the work done on the object. And you'll notice here, it's kind of interesting. It doesn't matter how far the object goes. All that matters is how much did the velocity change by. And so now when we look here, physicists have, by definition, said kinetic energy is an object's energy due to its motion. And remember, before we said energy is anything that can do work. And so if you have something moving like the head of a hammer, it can hit a nail and it can do work against the nail by driving the nail into the board. And so objects that are moving have energy because they can cause work. And so by definition, kinetic energy is equal to 1/2 mv squared, which is what the only difference here is we took the delta out of there. And so the kinetic energy something possesses is 1/2 m times its velocity squared. Now, to connect kinetic energy to net work, we will say, we'll put the delta V back in here, and work net will be equal to change in kinetic energy. And so then the equation looks like this. Work net equals F delta X equals MA X equals delta KE. And I should have had written in here equals 1/2 m delta x squared. So we now can set any of these up equal to each other in solving various problems involving objects changing speeds. So let's go to a problem dealing with that. And so again, I'm just looking at the problems that were in the textbook. Here is our example problems. We have 5.3. We have a driver in a car that has a mass of 1,000 kilograms, traveling at 35 meters per second, slams on its brakes to avoid hitting a second car in front of it, which had come to a rest. So it stopped. After the brakes are applied, a constant kinetic friction force of magnitude 8,000 newtons acts on the car. Ignoring air resistance, at what minimum distance should the brakes be applied to avoid a collision with the other vehicle? So in solving part A, we're looking at our variables. We have 1,000 kilogram car, initial velocity of 35. I didn't write the final velocity here, but it needs to come to a stop. So the final velocity is 0. And the frictional force is 8,000 newtons. So we can go back to the equations we just derived, and we have work net equals force times change in displacement, or delta x, equals the change in kinetic energy, which would be 1/2 m delta v squared. So we'll set those two equations equal to each other, and then we want to rearrange for x. So all I'm going to do is take this equation and divide both sides by f. And then plugging our numbers in, we have 1,000 kilograms times 35 meters per second squared divided by 2 divided by a negative 8,000 newtons. And this negative will cancel that negative. This negative should have been outside the parentheses. Those two negatives will cancel out, and we have a distance of 76.6 meters. Part B says, if the distance between, whoops, I went too far. If the distance between the vehicles is initially only 30 meters, at what speed would the collision occur? So we have 30 meters separation to begin with. Starting with the same equation, work, force times delta x, equals 1/2 m delta v squared. And in this case, I want to find final velocity. So I'm going to rearrange for final velocity. So I'm going to multiply both sides by 2, so I get 2fx. And I'm going to divide both sides by m, so I get 2fx divided by m. And then I'm going to add VO squared to both sides. So my equation looks like this. But we still have a v squared over here, so we're going to take the square root of both sides, and we end up with the square root of 2fx over m plus VO squared. Now it's just a matter of putting the numbers in. The square root of 2 times negative 8,000 times 30 divided by 1,000 plus 35 squared is 27.3 meters per second. So the car is going to slam into the other car at 27.3 meters per second. Now, we have another topic that I want to talk about here before we're done with section 2, and that's what is a conservative force and what is a non-conservative force. If we have only conservative forces, then we can use the equation that we previously had. If we have non-conservative forces, then we produce other energies that are not going to translate right into a change in kinetic energy. And so we have to account for the work used by the non-conservative forces. And more often than not, that energy turns out to be heat energy. So the definition we have here of conservative and non-conservative, a force is conservative if the work it does moving an object between 2 points is the same no matter what path is taken. So if we're talking about lifting an object and falling an object, for example, if we go down here, I have a picture of someone going up a high dive or going down a water slide. So both these, it's the same gal. So when she climbs up the ladder, she does so much work against gravity to get to the diving board. Well, if we ignore air resistance and we say this slide is frictionless, then the kinetic energy that she enters the pool with will be the same in both cases. So it doesn't matter if she goes straight down in a dive or she goes down the slide. But if there was friction, and so if there was friction, then as she would go down the slide, she would go into the water with a lot less kinetic energy. Well, where did that other energy go? The other energy went into the equation right here, where it's the non-conservative work, and the non-conservative work would be given off as heat in that case. And we'll study potential energy later. Another way is we can have a frictionless surface and we can still have a situation where we have non-conservative and conservative work. So let's say we're going to take a force and we're going to push this book from point A to point D. If we push it directly across, we do a lot less work than if we push it from A to B, B to C, and then C to D. So if all these are the same distance, then this is going to take 3 times the work to get it from here to here, but the net work is still from here to here. And so you would have whatever the network is to get from A to D. If you follow this route, you would have 2 times that work that is given off as non-conservative work. Only 1/3 of this effort goes into conservative work. I hope that makes sense. Sometimes what's conservative and non-conservative work gets a little confusing, but we'll cover various examples as they come up in our assignments and other examples that we'll do in our notes. So thanks again for watching. Hope this was helpful, and we'll see you again in a day or two.